This is what the data flow can look like at a company that is quite mature in its MLOps journey. This can be quite daunting, and as a new company in MLOps or a small company, you shouldn't really go for this at the first time, because that will be a large and costly project built on a lot of assumptions that you might not know is true for your organization. So as we go through the different components of this data flow, I will also point out not only what they are, but also why you need them and when you need them, so you know in what order to invest in them. So in part 1 of this video, we looked at this inner circle, where we have notebooks and simple pipelines or Python models, Python scripts to do your data exploration, feature engineering, training models, and evaluating models. If you haven't looked at that video, take a look at it later. It's linked in the comment. So today we're going to focus more about the things that are outside the circle, the whole environment that we have to help the engineers in their work and to continuously monitor the models that we have built. So in the first video, I talked a bit about when to use notebooks and when to use pipelines. I've seen a lot of people who are basically doing all of their ML development in notebooks, and then once they have a model which they are happy with, then perhaps they organize it into a pipeline to make it reproducible later. But I would rather encourage an iterative approach here, where you use the notebooks mainly for data exploration and feature engineering, which are highly visual and experimental work. And then as soon as you found something that you want to use, you integrate it in your pipelines or your scripts. And you do the experiments of different parameters here. You do the training and you do the evaluation here. And then you can continuously iterate between the two of them. And of course you have your code and configuration in versioned. For example, you can use Git here to version the code and the configuration. And when you do experiments, for example, if you want to try out different parameters, then create different branches and check out the different experiments. And if there is an experiment that turns out with good result, then you can merge that branch into master. But you still want the failed experiments, at least to some extent, in the code version control, so that you can see later what kind of experiments you did and why they didn't work. So going to the models. Once you have trained a model, what you want to know here is how to replicate the model. And I talk a lot about replicating models. And you might wonder, why do we want to replicate models? If we already have the models, we don't need to replicate it. But there are two different scenarios that I can explain when we need to replicate a model. So for example, it might be that we first have a deployment which is based on model number 1, and then we do some different experimentations. We find a model which we think is good, and we call it model number 2. Now we deploy model number 2, and it goes perhaps a few weeks, perhaps a few months, and then suddenly we start getting complaints about that our model has become very biased towards something, or that it doesn't work in certain situations. It might be that we have seasonal varieties. Our old model was well tested and had worked for many years, both during summers and winters. But our new model was deployed during the winter, and when the spring comes, it turns out that the new model does not work at all. in the summer. So in that case, we need to go back to the old model. And of course, hopefully we have the old model laying around somewhere and we could just redeploy that one. But now we effectively have a frozen model which we can't really build on top of because we can't replicate it, so we can't do any new improvements on it. Because the model itself is just the artifact of the code and data that was involved in building it. And now we need to reproduce that just to continue from the same baseline as we were before. And the other example could be differences in the input data to the model. So if we have a live production environment, we are collecting some kind of feature vector that goes into the model. So this goes into our model M1. And now we find out that we can add something extra to this vector. So we add a new extra field to the vector, which we can collect and send to the production environment, which can improve the accuracy of the model. So now we train a model number 2, which is using this new data to make better predictions. And after using this for a while, it might turn out that we cannot use this extra information anymore. So it could be that we see issues with computational complexity. It was too computational expensive to collect this vector. It could be differences in third-party APIs that this information was removed from the API and we can no longer access it. So now what we need to do is to go back to model number 1. And just removing this vector, we can find our old model. But it might also be that while having this extra vector, we have made new improvements. So we have a model number 3. So we still want to use these extra improvements between model number 2 and model number 3. But we want to apply them instead to model number 1, so we can go without this extra vector that we can no longer collect. So now we want to create a model 2 star, which contains the improvements of model number 3, but not the changes between model number 1 and model number 2. And in this case, you really need to see the history of your models and see what changed and be able to replicate it to apply the changes that you actually want to have. So just think about the very easiest way of doing this. One can imagine that we can say that we have an Excel document where we specify the name of each model and we specify what inputs was used to create this model. So to make this reproducible, we basically need to know what code was used. We need to know exactly what versions of the libraries was used to train it. We need to know what architecture was used, what evaluation methods was used, what hyperparameters was used, and what was the random seeds for the random data splits, for example, or other things that's using random values. And we also need to know exactly what data went into the model. So all these things, and possibly the data splits too, could go into the code version control, for example with Git. But how do we specify what data was used in the model? So in this case, we actually do need some kind of data versioning for the model, for the data set. And here we need both versioning on the data set level, but also on the file level. So for example, it might be that we have one folder containing images, which is what we train on. And one way that can change is the data set change, the collection of images change. we add new images or we remove images from the dataset. But it could also be that the images itself change. So for example, it might be that we have images with bounding boxes around faces, and someone has seen that one of the bounding boxes is incorrectly placed, so we correct that bounding box. Or it might be that we have an image that has been underexposed, or some kind of other image defect that needs to be changed. So we really need to know exactly what images, what collection of images and what exact images was used. And this is where the data version control comes in. So there are a lot of tools to do data version control. For example, if you're using Amazon's S3 buckets, you have versioning of the files there. So you can't get versioning on the data sets there, but you can get on the file level. But you could easily create version of the data set by creating a new file which references all the files and the file versions that belongs to that data set, and then you have different versions of that file. So that would effectively give you versioning of both the data set and the files. But the issue with that is that it's very hard to detect what changes has been made to the data sets. You want to see what images has been added, what images has been removed, and what images has changed. And this is where tools for data version control comes in to make that kind of actions much easier. So one of the tools that I usually go for when creating a new project is a tool called DVC, Data Version Control by Iterative. And that is very easy tool to set up. It's just as easy as setting up your Git server or setting up your Git project. You set up a DVC project. And now you have data versioning of your files. So this means that your model can reference the checksum in Git, the checksum in DVC, and then you can just check out the exactly same state and run the pipelines again to create the models. So this builds on the assumption that you have actually made pipelines which specifies the computation all the way from the input to the output. And this is why I prefer pipelines, or one of the reasons I prefer pipelines instead of notebooks. Because if you have a bunch of notebooks, even if you check out the exactly same commits, then you need to know what notebook should be run in what order, and what is the output and input of them. So for example, it might be that you have some kind of pre-processing that actually changes the content of the data, but not the structure of the data. So you can by mistake forget to run one of the scripts. And it is also much easier to test the whole thing when you have sequential pipelines or sequential scripts than when you have a bunch of notebooks. If you do one local change, you might not only want to see what local changes or what local effects does it have, but you also want to see how the effects propagate throughout the different steps. And with pipelines you can see that just running one command. So it saves you a lot of time. Okay, so now we know what models are used. So let's go to the data side. Starting all the way from the left, we have multiple streams of data coming in from different sources. So this could, for example, be that we are collecting some live data. We're collecting some live data from our customers. It could be that we have a QA department that are trying to replicate the hard situations and create we have a QA department that are trying to replicate hard situations in our lab and collect videos from that situations. And we could have a lot of other different sources. We can have different proof of concepts that are running at customer sites. And the data could be streamed coming in live directly through APIs, or it could be that we have actually people going out to our POC sites and collecting data on harder drives and then offloading it into our data system. So when coming in into our office building, basically, we want to store our data somehow. And I definitely recommend that you store the data unaltered directly once you get it. So you can call it a data lake or data storage or whatever you want to use. But the key idea is that the data is unchanged. It's exactly as you get it. You haven't enriched it and you haven't removed or filtered it in any way. And then we can have our data sets and databases where we have the data that we're actually using and actually interested in. So in between here we have some kind of transform. And this could contain cleaning of the data. It could contain altering different formats so we get the same format for all the data, if that's possible, or the same schema. And the reason that we want to do that as a separate stage and keep this is that if we discover that we have a bug in this transformation, for example, it might be that it has distracted some kind of information, lost some information, or created a change that was unwanted. Then we can correct this bug in this transformation script and rerun it on the original data to create correct data in our data set. If we did this transformation directly once the data come in, we have no way of correcting the errors that was already made in the data set. So that would be very dangerous. If you're acting in Europe somehow, you need to comply with the GDPR regulation. There are a lot of different regulations too in different countries and places and different industries. So you probably want to have some way of managing what kind of data you have. So for example, for the GDPR, a person who has his personal information somehow in our data set. It might be that we have images of this person. He has the right to request to be forgotten at any time, and then you must directly remove all the data you have with this person. So this means that you need to have some kind of database which specifies what persons or what objects are in different data catalogs or different images. And not only in one of the places like the data lake or the data set, but you need to know everywhere where it is replicated. So for example, if person A asks to be forgotten, he might have 100 pictures in the data lake where he is depicted. It might be 8 out of these pictures in the data set. And then it might be different copies at a different developer computer who have locally checked out data to experiment with. And in this case, you need to be able to remove all the data from all of these places on the request of that person. So that is what the data management is about. Then we have data dashboards. This I would say is mostly for long-term strategical planning. We might want to know on a high level what kind of data do we have in our data set, so we know how to direct our efforts to collect new data. So this could, for example, be distributions of data. If we have a face recognition application, we might want to know how much of our collected and annotated faces corresponds to men and how much corresponds to women, and so forth. So this would be a live dashboard or a report-based dashboard depicting what content do we have in our datasets. And a little bit similar is the data register. This mostly comes in at a later point when you're starting to create multiple different projects using machine learning. So it could, for example, be that we have our main application, which is a face recognition application. And then there is a decision that we should investigate the possibilities to create a face mask detection application. So what we want to do then is, instead of rushing out and starting to collect new data, we want to look at what data do we already have. Do we have something that we can reuse? And the point of the data register at this point is that it should be an easily accessible holistic view of what data is collected. And it should contain both the data itself and also the annotations. So for example, in this case, we might see that our facial recognition database contains a lot of images of faces. And then we want to know partly how are they annotated. Can we reuse some of the annotations and just enriched it with a bit more annotations to know specifically if it is a face mask on the image or not. But we also want to know the content of the images. So for example, are there any other faces that actually have face masks? Perhaps we have been collecting our facial recognition database during COVID and a lot of people have face masks. Then we already have the data there. So optimally we want some way here of visualizing the data too. So in the simplest case, this could perhaps just be an Excel file specifying what different data sets do we have, what is depicted in them, and how are they annotated. And perhaps a few different images from each data set just to show a rough idea of how they are actually looking. But it could also be a more competent tool, like for example, a bit more BI directed, like Apache Superset. So that has partly data exploration and partly data visualization. So the visualization can be used to see, dig more into the data and see what are the distributions of the data and so forth. And the data exploration are more to see what kind of data do you have. And this could possibly even be combined with the dashboards, so that the strategical and operational dashboards are created in the same tool that we can use for data exploration. So I think that's it for data. So moving on to the right side of the data flow, which is the production environment and the deployment. So what we should at very least have here is a development environment and a production environment. This might differ a bit depending on, for example, if you have edge deployed applications or if you have cloud deployments. But most of the core IDs is the same. And in the cloud environment, we could have these two environments. We could also have one development environment for each developer who is responsible for actually taking something to production. In the edge-based applications, this might just be, for example, a camera lying on each developer's desk. The important thing is that you have some place of experimenting with a model in a live setting without actually affecting customers. And the thing here about the development environment is that it is often broken because you use it for experimentation. So you might want to have also a staging environment here in between. And the point of the staging environment is that you treat it basically like a production environment. It should always work, but you don't have any customers there. So instead you can, for example, have your QA department looking at the staging environment. And here they know that it should always be working, but it is running the latest and greatest. So whenever they have time over, they can go there and test the application, do exploratory testing to see if they can find something that looks strange. That doesn't really work in a development environment, because there they need to synchronize with the developers and ask, is it an ID that I'm testing right now, or is it obviously broken? Going to the different deployment strategies. If you want to know more about deployment strategies, I recommend reading about cloud services and cloud native and so forth, because they know all about deployment strategies. Some of these are more applicable to cloud, some of them are applicable to edge-based too. Starting with shadow deployment, I would say this is especially if you are very unsure about the quality of your model. For example, it might be that you have a very small data set, so you have just validated it on a tiny validation set. In that case, what you can do is that you can make a copy of all the requests that you get to your system. And this works regardless if you're on a target device or if you're on a server. And you can measure how many of the predictions are actually differing from the old ones. And now you need some kind of some way of accessing data. So if you don't have any upstream connection from your devices where you deploy to, then this can be quite hard. Then you don't get any feedback loop, because what you want to do here is to look at the data corresponding to the predictions that differ between the old and the new model. So the new model is just running besides the old model, and it's the results from the old model that the customer sees. So the new model doesn't affect anything at all. It just makes the same makes prediction on the same data as the old model, and you measure in what situation does it differ. So it is basically a way of collecting new data that is concentrated to the situations where it differs between the new and the old one. Blue-green deployment. This is mostly for the cloud deployments, I would say. The idea here is that instead of replacing your model in the deployed code, you will instead create a new deployment environment next to the first one. So if you have your deployed environment here, which is actually running your model, and you have your customers interfacing with this deployment, then you set up a new deployment next to the first one, which contains your new model. And once this is set up and actually working, then you can just flip a switch, which redirects the traffic to the new one. And you still have the old one running and operating in the background, which means that if you see any issues with the new one, you can just flip the switch again back to the old one. And you don't remove the old one before you really trust the new one. So this depends a bit on how complex the deployment is. If you can just switch a model instantly, then it's not really any idea of having dual deployment environments, I would say. Then you can just as easily flip back the model if you need to re-roll to the last model. But for more complex deployments, it's really good to have. Canary deployment. This basically means that you're deploying to your customers gradually. Instead of flipping the switch for everyone at the same time, you do it a few customers at a time or a few requests at a time. So if something would be broken with a new model, you will see it from a few of the customers instead of affecting everyone at once. This actually works the same, or also works if you have edge deployments. For example, if you have people going into your website, downloading a new firmware and manually upgrading the product, then you will basically have canary deployments because not everyone will update at the same time. But if you're actually pushing out updates to your edge devices, then you might not want to push the updates to everyone at once, but you start updating in different stages. Going into A/B testing, this is basically for live system experimentation. And I would say the main benefit of this one is when you have some kind of automatically generating ground truth value, and when you have some complex thing in your model that you cannot predict in advance, that or some complex thing in your system that your model will affect. So for example, if we're talking about recommendation engines, then the recommendation is the output of the model, but you don't really know how the person will react to the recommendation. That's not something you can look on historical data, because if the old model hasn't done that recommendation, you can't know how the person will react to it. So you actually need to deploy the model and see how people are reacting and see how they are acting on that information you supply them, if it's in the way you want or not. So the A/B testing here is basically just that you put some customers or some requests through one model and some through another model, and you see which one turns out to lead into the best results. Then we have the multi-arm bandit MAB approach, which is basically like A/B testing, but it's more exploiting. So if you see that one of the A or B models turn out better, this approach will increase the amount of customers that are redirected to the one making well. So while this is very explorative, this is more exploitive. So there's the different deployment strategies. So now we start to get a quite good view over the whole flow in this system. So one of the last things to go through in this flow is the model monitoring. So once we actually have a model that is running in a production system, we probably want to continuously monitoring it and see how it does. Because one of the biggest issues with a system like this is that when we train our model, we train it on historical data. And then when we deploy it so it will act on data from the future. So this all builds on the assumption that the future is more or less the same as the past. So it could, for example, be that we have data collected pre-COVID and we're deploying our model during COVID. Or it could be that we have data collected in the winter time and we're deploying the model in the summertime. So what we want to do here is to look at the model as it is in production and have some kind of feedback loop telling us how it is doing. And in some situations we might have ground truth values that are automatically generated, like for prediction engines, for example. We can see if people bought the product we proposed to them or not. So in that case we should collect the ground truth values and see if the prediction was correct or not, and we can monitor the accuracy over time. But another thing we can do is to look at distributions. So we have something called model drift, which is basically when the time we apply the model isn't showing the same kind of distributions or behavior as when the data we trained it on was collected. And this can be split up into data drift and concept drift. So data drift is distribution changes in the data itself, while concept drift is that the mapping that the model is modeling has changed. So for example, if we take a scenario where we're trying to detect people in a camera view, but we also try to classify them as kids or adults, then it might be that if we collected all our training data during the summer, we learned that if a person is quite wide over the shoulders, it's an adult. If he's narrow over the shoulders, it's a kid. And that might be true during the summer, but if we deploy the model so it will be running during the winter, then people might be having thick winter jackets on them. And that might render this model behavior not true. So that would be concept drift, that everyone is suddenly classified as adults because they are much bigger from seen above, for example. While data drift could, for example, be if we have a camera mounted in a barn where it detects livestock. We mount the camera, we collect a bunch of images and we train our detector. Then we measure the accuracy of it and we see what kind of accuracy we have in detection rates. Then the deployment is done and the camera is sitting there month after month after month in a dirty environment where the lens actually gets dirtier and dirtier. So the image quality gets degraded and blurrier. And this can affect the model accuracy. So in this case we would see an incremental degradation in the accuracy of the model due to data drift. So what we want to do is to constantly monitor these three parameters and collect them into our database and probably show them on a strategical or operational dashboard where we can monitor the changes over time. And sudden changes in the data distribution doesn't need to mean that the model is not working. For example, if we see that suddenly a much larger ratio of people are classified as kids than adults, that might indicate that we have some kind of concept drift or data drift. But it could also just be that the sites have a festival for kids, for example. But if you see any changes there, it means that you should look into them. Okay, so now we have this complex system, and we say that there might be model drift. We might need to retrain our model every now and then because the environment and the data changes. So how do we do this? If we want to retrain often, then we can actually have an automated training pipeline which performs all these steps for us. If you need this or not depends on how much data do you have, what is the data velocity, the amount of data that you get every day, and what is the need to retrain the model. If you're, for example, using recommendation engines for videos, then it might be something that changes quite quickly depending on what videos are popular right now and different factors. So in that case, you might want to retrain your model every week, and you don't want a data engineer or someone sitting and doing all these steps every time. But in other cases, for example, if you're doing face detection, faces doesn't really change much over the years. So perhaps it's enough that you release a model a few times during its lifetime. And then you can do it manually, as long as you're doing all the tracking and data lineage, so you can see what was the path that was taken. But in the cases where you actually need to do it more often, you can have these automated training pipelines. And one of the things then is what should start the pipeline. So for example, we could start it on a schedule. We can say that every second week we're going to train a new model and deploy it. You could also say that we trigger it when we have a certain amount of new data or when the code is changed. So as soon as someone merges something new to master, we retrain the model. Or when we have at least, let's say, 1,000 new images in our data set, then we retrain the model. You could also trigger it on model decay. So since we're doing this feedback loop, continuous monitoring, if we see that the accuracy is decreasing a lot, for example, then we could automatically trigger a new training job, because we can assume that there have been some changes in the environment and hopefully we have collected new data of it. Or it could that we just have a simple button in the GUI that triggers this automatic pipeline, so that anyone on the operational side of the organization can trigger a new deployment. So the steps here are basically the same as what we have discussed already. The main addition is that since this is an unsupervised pipeline, basically, we need to put much more emphasis on the validation and evaluation of the different steps. So for example, we first do our data processing, and then we want to do data validation. And this is something that you probably do quite implicitly and ad hoc when you do a data exploration, for example. You see, does the data look good? Can I train my model on this data? But here no one is doing that, since it's an automated pipeline. So we need to have clear requirements on the data. So this could, for example, be to prohibit skewed data in our data set, or it could be to detect corrupt images in our data set, and so forth. Then we do the training, we do the evaluation and validation of the model. And then what we could do is that we can compare the new model to the old model and see what kind of data points are actually creating a different result between the models. And these data points could be uploaded to a data set. So this would give us a concentrated data set depicting just the data causing changes in this model. And we can use that to actually verify that the changes that the model validation says is good is actually good. Or it could also be from a fairness point of view. For example, we might see that some categories that we hadn't thought about becomes much worse, while the majority of the situation becomes better, for example. And you probably want to have some kind of manual QA in this process too, so that someone would get a notification a new model is available, and they could get, for example, a few subsample data points that they should look at the results and see, does this look good or does it not look good? Or it could be some exploratory testing just to validate that this doesn't spiral, that we actually have some human in the loop who can sign off and say, okay, this looks good to me. And then we have the automatic deployment. And here we can use all of these strategies. After deployment, we want to do a smoke test. Just a quick, simple test to see that the live environment actually responds as it should be, so that we know that the deployment actually succeeded. And then we go back to monitoring the model. So this is a lot of different steps, and you definitely shouldn't take all of them in one go. So think about what are the pain points in your development flow and your operational flow currently in your organization. But I would say that the most important thing to start with is to have a good environment to do the development of new models, and that you have versioning of your data and your code. And then you can build from there. And of course, if you have legal requirements and legislation, then you should make sure to take the data management into account so that you can comply with the regulations. And then many other things can be added iteratively as you find a need. For example, if you find that you're doing a lot of different development projects and have a hard time reusing the data because no one knows what data there is or how it looks like, then you should probably invest in a data register. If you find yourself doing frequent deployments and that it takes time and is error prone, then you should look into doing some more advanced deployment strategies, having different staging environment and so forth. So that's all for this time. Take a look at my other videos, and especially part 1 if you haven't looked at that one. We will look at the inner circle.